Hello again, it's Jason, solving LeetCode problems. Let's go. Remove duplicates from sorted array. Given an integer array nums, sorted in non-decreasing order, remove the duplicates in place such that each unique element appears only once. That's what removing duplicates, I guess, means. The relative order of the elements should be kept the same, then return the number of unique elements in nums. This is actually almost exactly the same as the problem that I did just before this one. Consider the number of unique elements of nums to be k. Get accepted, you need to do the following things. Change the array such that the first k elements of nums contain the unique elements in the order they were present in nums initially. Oh, yeah, no. It's not exactly the same. Such that the first and k elements contain the unique elements in the order they were present in nums initially. Remaining elements are not important as well as the size of nums. I think I have to... So what they're saying is the nums are sorted in non-decreasing order. So it's, let's say you have, well, duplicates will be next to each other, right? Because it's in non-decreasing order. F, 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 G, H, I, J. Right? Duplicates have to be next to each other because it's non-decreasing order. And if they weren't, right, if I move the duplicate over here, then it would have to decrease, okay, to get back to the duplicate. Okay. The relative order should be kept the same. I think this is just having two pointers into the array, and as you iterate through, every time you find a duplicate, you copy wherever the next non-duplicate pointer is, if that makes any sense. So in other words, I'll start off with my pointers I and J here at the beginning of the algorithm. You'll increment I, or maybe J starts off as being the next element after I. Let's do that. So it's like if I and J are different, we increment both. If they're different, we increment both. If they're the same, we just increment J. And then when we're done with that, we can copy J's thing down here. That's now D. And then once we do that, we can increment this. We need to copy, they are duplicates again. So now we have to increment this. It's not a duplicate. Copy this to here. Then I can go back to incrementing this. Wait, what? Yeah, I copy here, this to here. Okay. Copy this down to there. Increment this. Okay, now increment this. Keep incrementing it until I get to the G. Now I'm going to copy the G down to here. Oh, I see. Then I increment this, copy the H down, then now it's a duplicate, increment this, copy the I down, would be great if I could describe what I'm doing, but let's try to describe what I'm doing. I have a pointer to the next element that exists in the final array. In other words, one pointer represents every time that pointer gets written to is creating an element in the final array. Okay, the other pointer represents what does the J pointer represent? Let's go back to our example. A, B, C, C, E, C, D, E, F, 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 G. If I started my pointers there and here, okay, I could say that maybe J, like when I gets to here, we have to increment J all the way to there, because J represents the first element past I that is different. First element past I that is different. Okay, so conceptually, J is the first element past I that is not the same as I. When we find that, we can copy it to the position after I. Okay. Then we have to increment I. All right. Now they're the same, so we have to increment J until J becomes the first element after I. See, it's not the first element. That's not exactly what it is. It's not a good way to describe it. It's a good way to describe it. We have two pointers into the array. One represents the part of the array we are consuming, and the other represents what we are producing, essentially. So to think of it conceptually, I is the output, essentially. J equals the input. But it's just inputting from the array into itself. So when J and I are the same, you don't do, maybe I started out this way. J and I are the same, you don't do anything. No. I still want to have this. J and I is like, or like next, let's just say next output. Ah, yes, next number, right? So that, I think that's the best way to think of it. J is sort of the next number. This number, right? So then I is this number, B is the next number. And the algorithm is essentially, you can copy J into a temporary variable, put increment I by 1, copy the temporary variable into where A is, and you have to increment J. And the only difference is that when you increment J, if it's the same value, keep incrementing. So if we say for this number equals 0, I'm going to take care of edge cases in a second. The numbers could be length 1. for let this number equal 0. Next number equals 1 number index. This current, I would say current index, next index, okay? And then we have some condition, and then we have some increment. And inside our loop, we basically say, stop it. Current index plus nums current index equals nums next index. Okay, so I changed where current was, so now I'm storing into the current whatever the next is. This is the transition. Then advance to next. Advance next index. And that's it. I don't need this case. Okay. And the let advance next index equal a function, and that says what we want that to do. Let's going back to our example. We would say when we're advancing, if current index is B and the next one is C, we would of course increment current, store the contents of there into there, and then we have to advance, but like let previous value equal nums next index. We're advancing next index here, and then next index plus plus, or we'll just say like while nums next index equals previous value next index plus plus. This takes care of, I increment j once, okay, I'm storing the previous value, which is this, but then I need to keep advancing it until it's not equal to the same thing that it was before. Okay, that's the end of that function. That advances, so we have two pointers again, the current index and next index. That's this one and this one. Okay. The only part that I need to work out are the exit conditions from both of the two loops. We of course would stop. Let's say in this example that I have here, you would advance this, store the letter D here, advance this, you would advance this, store the letter E here, advance this, store the letter F here, advance, keep advancing, keep advancing. Okay, advance this, store the letter G here. If you try to advance, you get to the end, okay, you're done, you ran out of stuff. J is always going to get there first, okay? J will always get there first because J starts out larger than I and never doesn't get incremented at least once, right? So in here, at some point, J will finish up. So when J finishes up, I will basically return. Okay, let's think about this. Conceptually, I should return. Because I've probably been going to put this, right, here. Okay. Right? That's an interesting way to put it, and I think that means that the next index starts at 0 because, of course, we test the condition before going into the loop, right? And then this needs to return a value. If I almost make this like a do while. Remember those? Do that while that. And then if next index equals nums, return false, maybe. Right? Otherwise, return true. We have more to do. Okay? Let's think a little bit more with our brains. Let's try this algorithm with a test case. Oh, by the way, I need to return something. I let current index equal 0. The reason I need to do that, we'll return as the size, I think. I want to output K. Doop doop doopy doop doop dbd doop doop. Okay. Let's think about edge cases. That's one edge case out of the way. There's not going to be any duplicates. Let's say this is your array. We start off, start the clock. Current index is that. I'll change the letters from I and J to C and N for current and next. We start them both at 0. The first thing we do is advance the next index, which just copies the array value to itself. And then it increments next index to there. It is the same, okay? So then we go back and increment it again, and now next index equals nums.length. So we actually return false from this advanced next index. Never actually. What? Oh yeah, no, it does, because it does this first. Oh, it does this first. I think that's fine. Returns 1, and that's the right answer for that array, because it'll just go off the end. But if I have AB, then I start with CN. Okay. Then the first thing we do is increment advanced next index. I think I do have a problem, and that is that it will advance it once before copying, so I get rid of the first element in the array, because I moved this here because it used to be here. This returns, I hate this, but like, if this returns true, okay, let's rename some variables here. We have 2 pointers into this array, current and next. I think I originally wanted next to start as. I don't know why I changed that. Okay. And I think it's probably better if I say while next index is less than nums.length. Okay. Advance next index. Forget about this. Okay. The reason I'm incrementing current index first, right, is because like it gets incremented to the place where current and next is such a weird concept, but basically it's not. Every time you run through the loop, you're sort of advancing the system by 1. So to advance it, the copy, the read, write, head, right? That means to advance it, you have to move both. I'm only moving one I'm moving this 1 in the body. Okay, I move this, then I move the next. So, only thing here now, do next index plus plus. I don't need to return a value. I just say while next index less than nums dot length and that. So forget about returning a value here. When I advance the index in this part of the for loop, I just tracking the whatever it was before, so the only reason I do that is because I need to know if I need to index it more times, increment it more times. Then I do at least one increment. Then if it's the same, I keep doing increments until it's not the same, or if I run out of room, then I ran out of room. Then I quit. Either way, the only thing that's changed is nothing, is next index. So then, since I just ran this statement at the end of my loop, I have to do the test before going into the loop, and next index will be equal to nums.length, because that's why we exited here. It should work. Garbage collection. JavaScript heap out of memory. Okay. That's interesting. Is that because this needs to be an OR? I think that's why. No. That is the opposite of true. It runs out of memory. That's interesting. Why would that happen? What the heck is... Where is it accumulating memory? Case 1, case 2. The judge will test your solution with the following code. Calls your implementation. Assert k equals expected nums dot length. Go through expected nums and assert this. Okay, so 1, 1, 2. 1, 1, 2. I think I can do it so it only tests this case. Yeah, even that case, even this case didn't work. So this isn't true, so we don't get to that case. This is our function. Current index is 0, next index is 1. Starting there. Let next index... Oh, wait, why do I have this? Oops. I think I was going to get rid of that. That is the wrong answer, though. So let's see why it's giving me the wrong answer. The next index 1, current index 0. next index less than nums dot. Okay. Of course it is. Increment current index, so that becomes that. Then I copy that to there. Because my algorithm that I came up with assumes the reason that this broke is because I did not pick a good set of test cases. The actual thing I need to do is not set next index to 1, but rather set it to, could set it to 1 or 0, it doesn't matter, but then I have to call advance next index to find the first element that is not the same as the first element that's not the same as the first element of the array. Okay, that was it. That was an interesting problem. A little tricky. All right.